to discuss the topic of VLSI Design Flow, a complete overview. So in this presentation, we will be discussing what all steps are there in the process of designing a IC chip, which is basically referred to as the VLSI Design Flow. So we'll be starting with the introduction part. First of all, we need to know what are the basic definitions which are there in this VLSI design flow. So first of all, as you all know, ICs, which is referred to as integrated circuits, they are the heart of our modern electronic devices, be it your mobile phones, your laptops, whatever microprocessors are there, FPGA units are there. In that, I mean, they act as your IC, and in order to make that IC, you need to know the steps of it. So the entire process of designing an IC is referred to as your VLSI design flow. So basically, what is VLSI then? VLSI is very large scale integration. Like when you are designing a circuit, when you are designing a circuit, there are certain integration levels which are there. So depending on how many transistors you are having in one chip, depending on the integration level of that, you define these type of integration levels that we have, which is in our case is VLSI. So basically this VLSI design flow is a step-by-step process which is starting with system specification and finally ending with the packaging and testing of our product. So our final product is basically an IC, and what all steps are there that we are going to see in this presentation. So now the question comes, why we are doing it? What is the goal of having this VLSI design flow? The primary aim of our design is that we need to minimize the design cycle time while maximizing the quality and reliability of the final product. So in our case, the final product would be IC only. So basically, design cycle time means the time it takes to make our final product, the time it takes to go from a system specification to packaging and testing, that is defined as a design cycle time. So in order to produce more number of chips, or time constraint is always there, so we need to minimize this design cycle time also, while at the same time we would not be compromising with the quality and reliability of our final product. Now, prior to starting with the steps that are there, there are two things the design flow can be divided into two types. One is top down design flow and the second is bottom up design flow. So what is there in top down design flow? Basically, as the name suggests, you will be starting from the top, like you will be starting with the high level specification, and then you will be refining your design to the lower levels of abstraction. Like you will be having a complete overview of your design, and then you will be step by step, you will be refining your process. So that would be referred to as top down design flow. The complement of it, like the opposite of it, is bottom up design flow. In that, you will be starting from the lower level and then you will be moving to the higher level. So basically, you will be beginning with individual components or modules which are there, and then those modules are combined to form the lower system. So it is basically an iterative integration from lower to higher levels. In the top down approach, we were going from the higher to the lower level of abstraction, and here we'll be going from the lower level to the higher one. So this is the VLSI design flow that we have been discussing so far. So as you can see from here, that the design process, it is starting with system specification, and finally we are doing the packaging and testing of our IC. On the left hand side, you can see the corresponding diagram. We'll try to see what is happening in each of the steps which is there. So that is shown over here. And apart from that, one physical design step has some more steps inside it. Like this physical design process would consist of some more steps that have been shown on the right hand side. So what we are going to do, we'll be discussing each of the steps in detail in order to understand the entire process. So next, what we have, the first step, as I have already told you, that the first step of the VLSI design process is system specification. So what is there in this that we need to see? So first of all, you would be defining in this step, like if I give you an example, whenever you are buying something, you need to tell your seller that I want to have this these are the specification, or these are the things that I need in my product. So whenever you are going to buy something, you will be having a set of specifications in your mind that you want to tell your tell your seller. So in a similar way, in the VLSI design flow, the customer tells you that these are the functionalities, these are the specifications that I need to have in our product. So after getting feedback from the customer, you will be preparing a document, like it is a you will be getting an idea about what the customer wants. So in that case, what would be our goal? Our goal is to understand the functionality, the performance requirements which are there, dimension, and the technology we are going to use. Depending on that, you will be saying, okay, what team members do I need to have, what expertise do I need to require. So that would also be decided. So basically this system specification would decide the foundation. It would decide your final outcome. It would act as a foundation for the entire design process. Then the second step is architectural design. Like you have your specification, you have finalized your specification, you have understood your customer requirements. Now we are going to see that what architecture would I be using, like how the blocks which are there, like in an IC you have multiple blocks which are present. So how I would, which blocks do I need to have, how many blocks which are there, that I need to define at this stage. So basically you would be defining the architecture of your IC, be it analog or mixed signal blocks are there, memory blocks are there, codes are there. So that you need to define at this stage. So also at the same time, you will be taking some decision on what protocols I can use, how many pin out would, how many pins are there, packaging and everything. These things are decided in this architectural design part. So at the architecture level, you are defining your IC. So this is the step that we have. The next step that is there is functional and logic design. So here we'll be talking about the design entry part. Now you have understood the specification, you have understood the architecture of it. Now you need to see how I can implement it. The IC process that is done using certain tools. So how I am going to enter my design into the tools. So that is referred to as design entry. So in VLSI we have two ways of doing it. Either we can use hardware description language, or we can use the uh, semantic based tools which are there. So in hardware description language, as the name suggests, these are the languages which are used to basically to write the code. So you will be defining the connectivity and timing at RTL using hardware description languages. So mainly Verilog and VHDL are your languages which are used in this step. So there are multiple tools for doing that, in which are available in industry, so that we can use. So basically what you are going to do, you are going to do certain simulations, you are going to enter your design, then you are going to do simulation in order to see whether my design is working properly or not, whether my blocks which I have designed are they functionally correct or not. I need to implement the functionality of my blocks. So that would come over here. After this, the next step is my circuit design. So as the name suggests, you will be making circuits of the, the previous step would act as an input to this one. So you will be seeing what at circuit level, you would be translating your register transfer level RTL to the circuit level, which is your gate level netlist. So here you will be optimizing the performance, power and area, and multiple tools can be used. You will be again doing certain simulations and all. So basically you are seeing your circuit in the, you are basically looking at your design in terms of the circuits that we have. So after that, one more step, another step that we have is physical design. As I have already told you in the initial slide, that this physical design consists of multiple steps inside it. So first of all, we need to understand what is physical design. So physical design is basically, it is the process of transforming a circuit description into the physical layout. So basically, in the previous step, you describe your circuits, that what circuit is there, what gates we have used, what components we are using, that we have described. Now the actual process is there, which is that we need to convert our circuit description into physical layout. I mean, when we are going to go on the silicon part, how the my circuit would be translating over there, that we need to understand, that we need to do. So what are the main steps over here that we need to understand? The steps which are there, let me show you uh, the steps which are there. So you can see the physical design process. Initially you would be partitioning, you will be dividing your entire area which is available to you. First of all, you will be dividing it into multiple areas, and so that is referred to as partitioning. As its name suggests, you are partitioning your design. Then you will be having a chip planning, or you can say floor planning, like how my components would be arranged on that area, that we need to plan. So that is referred to as floor planning or chip planning. So we'll be seeing how, how the, if I mean you will get an approximate idea of how the components would be placed on the chip. And the next step that we have is placement. So in placement, you will be placing your the blocks that you have. You will be deciding which accurate position of the blocks that you have, you would be deciding in this step. So after you are done with partitioning, chip planning, and you have finalized the location of your blocks or modules, then you will be checking, you will be doing clock tree synthesis. As we all know that for our design, we need to have clock, like we need to we need to have certain synchronization at what time what block would be operating. So that we will be needing, in layman terms if we say, we'll be using a clock. So how the clock is distributed across the entire area, that is decided in clock tree synthesis. And then finally signal routing is there. You will be connecting the components, all the components which are there, there must be some interdependence amongst them, that you need to do. You will be connecting them. So that is referred to as signal routing. And then finally we'll be ending it with timing closure. So after you have done your placement, you have done clock tree synthesis, signal routing has been achieved. After that, we'll be doing timing closure, like in terms of timing, how my circuit is operating, how my design is operating, that we need to understand. So this is a brief overview. Like if you go into the details of each one of these steps, there are multiple ways of defining it, and there are multiple algos, multiple things which are there in each one of them, that you can elaborate at your level. Then after we are done with our physical design part, so basically what you have done in the previous step, you have converted your design into a layout. Now we need to do verification, like how is my layout working out, is it fine? We need to verify our layout. So in order to do that, that process is referred to as physical verification. So there are multiple ways of doing it, like we have design rule checking is there, LVS is there, layout versus schematic. So these are the techniques which are written over here. These are the ways of verifying your design. So in why we are doing this physical verification, because we need to ensure the functionality and the manufacturability of our design. See, you have your specification, you have designed up, you have designed the architecture, you have defined it, and you have arrived at layout. Now you need to ensure whether it is working fine or not. So you will be ensuring functionality and manufacturability. So you need to optimize your layout. If any issues are there, that you need to resolve in the case of physical verification. So whenever you are doing something, you verify at your level. So in a similar way, if you have a physical layout, you need to verify it. So that is referred to as physical verification. Then the the final steps of it would involve fabrication. So basically, you have a GDS2 file, you will be giving it to the foundry. Fabrication facilities are there, they would do the actual manufacturing of your IC. So there are multiple processes which are involved, like photolithographic which is involved, masking is involved. So that way they would be, the design that you have, the layout that you have, they would be transferring it to the actual manufacturing type part. Like you get your IC, so that IC is obtained in this particular step. So there are multiple foundries which are available, and basically silicon wafers are used to do the process, mainly used to do the process of fabrication. Then at the last we have the packaging and testing. Now you have your what we call it, you have your IC product, like you have fabricated that. Now you need to do packaging of it in order to provide some protection, and you need to check the testing, like you need to test your chip whether after manufacturing whether it is working fine or not. So in order to check the chip, you do testing, and there are multiple packages which are there, like DIP, PGA, BGA. These are the multiple types of packages which are available in order to make an IC, final IC chip. So the primary aim of our testing process is that we need to ensure that the initial design specification that were there, they are specified. Like if you remember, in the first step we told that we need to elaborate, I mean we need to specify a specification. So here at the final product, when we have obtained our final product, we need to ensure whether we are meeting those specification or not. Is there anything, something is left out or not, that we need to check. And also we need to have defect free product. I mean it should not happen that my chip goes to the customer and then it is not performing well, it is having some defect. That would not be I mean that would not act as a good product. So in order to ensure that we have met the specification, and at the same time we have made a defect free product, so we do testing. And I mean the packaging and testing is done. So testing is basically to ensure the design specification and in order to have defect free products. So in conclusion, what we can say that the VLSI design flow, the entire steps, they are very important for modern electronic devices, the devices that we are using day to day life. All these devices has been made using the steps that we have discussed today. So through execution, the flow ensures that the final product is efficient and reliable at the same time. So we need to create ICs which consume minimal power and area, and they meet the performance standards. So this was all about today. Like today we had discussed this VLSI design flow. Thank you so much.